So we know that nothing can go faster than light, and that time slows and objects get contracted when they travel really fast. But imagine this. You have a limited amount of fuel in a rocket, and every time when we fire a burst of fuel, the rocket gains some speed and goes faster. And with more and more additional bursts of fuel, it gets faster and faster. And eventually, it can go faster than light, doesn't it? So the idea of cosmic speed limit was established in the beginning of the 20th century. But doesn't it contradict with how we think the world works? Like nothing can go faster than light. So today we're going to back up these two claims with some solid example evidence and understand why they're true. So the two facts about how the world works can be derived from the result of the Michelson-Morley experiment, which to many at that time was considered as a failure, but it was a great failure. So motivations behind the two, there's some motivations behind it, the two ideas of velocities and light. So first I'll show Thank you.
Things from a particular point of view. That is, from a particular frame of reference. Things look different to us under different circumstances. At the moment, things look peculiar. You're upside down. No, you're the one that's upside down. No, you're upside down. No, I'm not. He's the one that's upside down, isn't he? Well, let's toss for it. All right. Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now. My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands. This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving.
So as you can see that when we think we're standing still, we might not be standing still because of the surrounding of us that is moving. It's a really cool video, and it has 2 parts to it, and like if you have nothing to do, it's really fun to watch. So at this point, you should know that like no matter what speed you're going, you cannot do any experiment to prove that you are moving or you're standing still. So imagine this. We learned that from last year that when you're on a car with the open top and you're moving at a constant speed, when you throw the ball up, does the ball leave behind, or do you catch the ball?
You catch it.
You catch the ball because of the inertia. When an object isn't being pushed or pulled, it continues to move in the direction it was going. So how about this? This time you're on the bus with no windows at all, so you can't tell whether you're moving at a constant speed with the bus. So you can't tell whether you're moving or not. And I'm standing outside on the ground, and both of us argue that we're standing still. So is the ground moving? Which of us are moving? You would say that I'm standing still, but the ground moves. The ground beneath us spin around the Earth 300 meters every second, and the Earth orbits around the Sun at around 30 kilometers per second. And the Sun moving around the center of the Milky Way 200 kilometers per second. So basically, none of us are standing still right now. We're both moving. So each of us are in a unique frames of reference that seem to believe that we're not moving. We can claim that each other is moving, but we're both standing still. So this time, here's another example. You're at the back. This is you on the bus holding a ball, and I'm standing outside on the ground. You throw the ball, and it hits the windshield. You time how much time it takes for your ball to hit the windshield. You say 1 second, and the distance from you to the windshield is 9 meters. So distance over time, velocity, you get 9 meters per second. That's how you think the ball is going. But now let's look at it from my perspective. When I can see you, the bus, and the ball throwing, and the throwing action of the ball moving in one direction. I measured the 1 second time interval and the distance the ball has traveled. But here's the difference. The bus windshield is moving forward as the ball is throwing. So to me, your ball is moving at a more distance. And say the bus is moving at 21 meters per second. So to me, your ball is moving at 30 meters per second. So this is Galilean relativity. So it's meaningless to say the ball is either moving 30 meters per second or 9 meters per second. So we need something. So we measure different speeds. So we have to say that the ball was moving 30 meters per second relative to the ground for me. And, it's 9 meters per second relative to the bus. So now after velocity, we'll move on to light. In the 1860s, James Clerk Maxwell made up a James Maxwell equation describing the electron magnetism. So there was a special quantity that he came up with, which is like this. I don't know what to say. And normally we round it up to 3 million meters per second, which is what we know as the speed of light, also the little capital C. So light travels at c. So can anyone tell me what the problem is? So light travels at c, but it has to be relative to something. Like it's meaningless to say that light travels at c. Something must travel at something relative to something. So light is a wave. And wave needs a medium to propagate through it. So there's no water wave without water, and there's no sound wave without air, wall, or something. So we can't have light traveling through without nothing. So then we have luminiferous ether, but people normally call it as ether. And we say that light travels at 3 million meters per second relative to the ether. So it also uses to explain how light is able to travel through the sun and other stars to the Earth through like what otherwise would be empty space, but ether fills the empty space so light can travel through. So we say that if you're at rest relative to the ether, you will measure the speed of light as 3 million meters per second. But if you're moving relative to the ether, you will see the light traveling at a different speed, which makes sense from what we discovered in the physics. So, which is right? You cannot do any experiment to prove that you're moving, or you can tell your motion through the ether. So does that idea of absolute standing still doesn't exist? Or light travels at speed through the ether. So we need an experimental evidence. So that's why we have the Michelson-Morley experiment. It was in 1887 where Albert Michelson and Edward Rayleigh, they made up a super precise setup. This experiment. So you can see that they first have a light, like this thing produces light. There's a semi-transparent mirror, and then there's two more mirrors here, and here's a detector. So I'll say. So the light goes out, splits into two, reflects from the mirror, rejoins, and then connects and goes back, like hits the detector. So if the two split beams arrive to the detector at the same time, we'll see a bright spot in the detector, meaning that the two beams were in phase. But so in here, we'll watch this is change the speed of the ether and the light. So you can see that after they rejoin, the green arrow is moving faster than the red arrow. And it doesn't show in this animation, but in the actual experiment, the detector will not, there will be a dark spot in the detector, meaning that the two beams are canceling each other out, that they're out of phase. So here's another animation that would explain it a bit more. So there are two swimmers, the red dot and the green dot, and they're swimming towards the line here. So, oh, sorry. So this is the first one, where they're swimming, nothing is moving, and they're just swimming towards the direction and then coming back. But as we know that if the experiment is done on Earth, the experimental setup would be moving through the ether. So as Earth is always changing direction and it's moving around the sun throughout the year. So the entire experiment moves the ether in this way. So imagine this box moving this time, such as the Earth moving. So we can see that the green spot arrives like faster, and the red box goes back to it slower because the yellow box is moving this way, and it takes a longer distance for the red dot to move back to the thing. So similar to throwing the ball and trying to catch, similar to throwing the ball and hoping the ball to catch up to the windshield. But there are no speed boosts for light, so we can throw the ball harder so the ball will move faster. But there's nothing like this for light, since light must travel at speed relative to the ether. So one light beam would take more time to travel to the mirror, and it has a longer distance. But if we rotate the experiment such a unique angle so that the light beams travel at the same distance through the ether, and they would arrive at the detector at the same time.
So that's the toughest thing to do. This was the most difficult experiment ever performed. So hard to do.
the one where the two arrows arrive at a different time. So now I changed the angle. It's 30 degrees. So we'll see what happens. So it's at a special, like, unique angle. So with the same light speed and the same ether speed. Okay, it should, I think something wrong, but it should arrive at the same time. Yeah. And then, so I'll go back. So we can tell that some dark spots are on the detector at some angle and some bright spot at some other angles. So it's proving that will prove that either does exist, right? But so that it would, then we could say that it is possible to detect if we're standing still or not. But the result after they do the experiment, they found out that no matter how you turn the experiment, it did not really change significantly. So they failed to detect the ether. But was it really a failure? The speed of the ball is different, and light is traveling at c regardless of how fast the person on the bus is moving. So the experiment can be moving at any speed, and light will still look like it's traveling at c relative to the experiment itself. And everyone in every frame of reference measure light to be c. So for every one of us, we see light at the same speed. And Galileo, but yeah. So here's one more example. So say you're in the middle of the bus, and you're trying to, you're showing a light, like, circle going out. And you say that the light hits the back and the front of the bus at the same time. But to me, who is standing outside, I say that since the bus is moving at a constant speed, I say that it hits the back of the bus and then the front of the bus at different times. So why do, like, sorry. And why does this happen? This is because we've made certain assumptions about, like, the behavior of space and time as we live in our slow life, moving slowly relative to anything and everything we interact, and we do not usually encounter relativity in our everyday life. So we do not grow up thinking in relativity, but we can learn to. So the problem of simultaneity can be resolved since we know that it must be true in the Michelson-Morley experiment. So let's say this is the last example. Let's say there's a light clock that works like perfectly, hypothetically clock. It works by having a beam of light bounces back and forth between two mirrors. So once it bounces back and forth, there will be one fix. So at the same time, you have the clock in the bus and I have the clock outside. So to me, your clock is moving since the bus is moving, and to you, your clock is not moving at all. Basically, so I think that your clock will move slower than, like, will have less ticks than me. But when we think of your perspective, you think that you're the one moving still and I'm the one that is further. So you think that my clock is moving slower than yours. So how does this work? So everyone measures the light of speed as speed of light as c, regardless to the state of motion. And so we say that we should see each other as contracted and can agree on both simultaneous events. But in a mathematical form, like, the paradoxes cancel each other out. So it proves us that relativity is real. So, and we also say that when there's particles that naturally decay tend to live longer when they're in particle accelerations, because they move faster and they go relative to the rest of the world, so that they live longer. But their lifespan had increased because, according to us, their time is slower. So for conclusion, we live in a world which makes no sense, but we don't because we don't directly encounter outside of relativity in our everyday lives. But this is the true nature of how the world exists. And it is very confusing and complex, but it is here and real and